Today's lecture is going to be on the introduction to principal components analysis. It's a new chapter for us, and in short form, principal component analysis is referred to as the PCA in the literature. So, this is what I want to introduce today. Now, before we introduce this, let me tell you about the basic motivation of this technique. Okay. First of all, we have to understand that, and thereafter we will be presenting the theory of the principal components analysis, and once the theory is known to us, we will also see that what is its relevance to the neural network. In fact, as you will see later on, that the principal component analysis problems are easily solvable using the artificial neural network. So, that is where it has assumed so much of importance in the study of neural network. It is a very important thing. Now, one thing which has been discussed over the last chapter is that we deal with the input data, and the input data is in the form of an m-dimensional vector. So, we consider x vector to be an m-dimensional vector, which in general we know is non-linearly separable. So, to make it linearly separable, what we do is to map this m0 dimensional vector, okay, into a higher dimension, okay, because we argued last time that in higher dimension the separability increases, okay, and then we can, once the separability is ensured by mapping it into a higher dimensional space or by mapping non-linearly. Not that we always require a higher dimensional mapping, but what is essential is we need a non-linear mapping, okay, preferably on a higher dimension, and then the classification accuracy definitely improves, okay, and the classification is to be carried out based on that. But there are some cases where the dimensionality of the input itself is considered to be excessively large, okay, and in such cases the problem that one has to face is that, if we have to deal already with a large dimensional input vector and we want to map it non-linearly into an even higher dimensional space, then of course the size of the neural network that increases enormously, okay. So, where the number of, where the dimensionality of the input itself is very large, then our objective should be to reduce the dimensionality. And how? There we have to find out that whether in the input data itself, okay, there is any redundancy that is present. If supposing it is m-dimensional input, then what we have to find out is that within that m-dimensional data that we have got, is there any redundancy whereby we can, let us say, we keep some of the inputs, let us say we keep m0 number of inputs we keep out of m, and we discard where m0 is a number which is less than m, and we discard the remaining m0 minus m data points altogether. Is that possible to do? it is only possible to do if whatever we are eliminating, okay, is really something very insignificant, then we can afford to do. But given an m dimensional data set, let us say that we have got data, I mean this x vectors composition is, let us say, x1, x2, x3 all the way up to, let us say, here x m0, then x m0 plus 1, etc., up to, let us say, xm. Supposing this is the composition of the vector, and we say that this m is a very large number and we do not want to deal with such a large number, we want to reduce that to m0. In that case, what we are simply deciding upon is that we will keep this much and we will truncate the rest. The rest we will not use at all. Not use means, okay, we will keep it as 0 data, or to say in the representation of the data, these m0 points should be good enough for us. We do not require the remaining m minus m0 number of data points that we have got. Now, we can do that only when we are eliminating some insignificant data. Now, how to make sure that whether something is insignificant? Well, that analysis has to be done, because otherwise somebody giving me an m dimensional data and I just decide on my own that, okay, I will keep the first m1 number of points and all the remaining first m0 number of points and all the remaining data I will truncate to 0. If I do that, definitely what I am doing is I am introducing error, right? And what will be the amount of error that I incorporate in that process by simply chopping off the data mercilessly? In that case, the mean square error that I will be incurring in the data, okay, should be equal to what? Should be equal to the variance of the data, okay, which I have eliminated. Okay. So, the MAC will be equal to the sum of the variances of the elements, sum of the variances of the elements which are eliminated. Okay. So, that should be our mean square error. Now, naturally we can afford to tolerate some definite mean square error if the sum of the variance of the elements eliminated, they are a small quantity. Only if it makes some sense that, okay, whatever we eliminated, okay, results in a very insignificant amount of mean square error. Now, how to do that? Because we are in the x vector space. X vector is an m dimensional space, and how do we decide that whether it contains anything that is insignificant or not, or how do we decide that, okay, this way we will be picking up the first m0 number of significant coefficient. So, for that matter, unfortunately the x domain will not be of use to us, because we cannot say that, okay, the first m0 points are important and the rest m minus m0 points are not important, because the next data that arrives, the next pattern that we choose, okay, could be having more significant information here. Okay. Some other time maybe, some other points are important. So, naturally in the x domain we cannot really decide that something is of low variance, so we can eliminate that. So, to do that, what we do is that we have to map this x vector, okay, into another vector space, which we achieve by transforming this x vector. So, let us say that x is an m dimensional vector. Okay. So, if we can design a matrix, let us say that we design a T matrix that is m by m, and we just pre-multiply the x vector with this T matrix. Okay. Then what results? This is x is m dimensional vector. So, what results is another m dimensional vector. So, this is the new vector T x is a new vector, let us say this is x n, that is a new or x new, let us say. So, we have got a new vector x new, and it may be possible that in the transformed space, I mean if we transform this x into x new, could be that in the transformed space out of the m number of points that we have got in x new, okay, m0 points are significant and the rest m minus m0 points are insignificant. It may be easy for us to decide in the transform space. So, that means to say that we have to very cleverly design this transformation T, all right. In fact, this transformation design is something that we are doing in several fields, okay, especially several fields of electrical engineering, electronics engineering, I mean fields related to the electrical sciences. We require the design of such transforms, okay, enormously. One of the things which all of you must have done is the use of the transforms, okay, use of orthogonal transforms, okay, in order to I mean which serves as the basis functions, and we can reconstruct signal on the basis of using those orthogonal functions. We know about the Fourier transform, we know about the cosine transforms and its discrete versions in the form of discrete Fourier transform, discrete cosine transforms, etc. All these things are giving us this T matrix in some form. Okay. It is based on some definite kernels, okay, which exist. But one difficulty is that this is based on some fixed kernels. I mean, you talk of the DCT or DFT, these things, they are based on some fixed kernels which are, say for example, in the case of Fourier transform, the kernel is an exponential, complex exponential kernel consisting of cosine terms and the sine terms, or the discrete cosine transform that consists of the cosine terms used as the kernels, okay, as the basis function. The difficulty is that if instead of designing it based on the fixed kernel, okay, we can design our own kernel and try to find out the optimal kernel or the optimal transformation, okay, so that in the transformed vector that we are getting x new, okay, it is possible to find out, I mean an optimal, I mean if we can find out an optimal transformation T such that in the x new, okay, if we eliminate the last few points, okay, then we will be eliminating the terms with very low variance, and eliminating terms with very low variance will lead to lower mean square error. So, that we should be able to use those kind of transforms, okay, in an optimal sense. So, that is exactly what we are attempting to do. So, now our main objective will be to design a good transformation function T, okay, such that in the transformed space, that is in x new that we have got, okay, we have got low variance terms which can be easily chopped off. Okay. So, with that motivation in mind, we are designing what is called as the principal component analysis. Okay. And I will also touch upon the point that why at all it is called as the principal component, what is so principal in it. Okay. Those things will come little later on, okay. But let us first of all develop the theory, okay, which will enable us to design a good transformation T. That is what, with that motivation in mind, let us proceed. So, what our objective is to maximize the rate of decrease of variance, because if we can maximize the rate of decrease of variance, in that case the last terms that we have got, okay, they will be having very low variance and we can easily get away with it. That is what we are looking for. Okay. So, to give the mathematical analysis for that, let us consider an m dimensional input vector. Okay. In fact, that will be treated as a random variable used as a vector. So, this is an m dimensional random vector. Okay. And furthermore, what we assume is that the expectation of this x vector is equal to 0. Now, this can develop some doubt in your mind that okay, can we assume all the time that the input that we are getting should have an expectation equal to 0. That means to say that the positive coefficients and the negative coefficients are equally likely. In practical data, it is very often not. Okay. In fact, most of the cases it is not the case. You may be having always some positive values defined as the elements of the x vector. In such case, what you do? So, what you do is that simply you subtract the mean from the individual elements. If it is not a 0 mean random vector, you make it 0 mean by subtracting the mean from it. So, if x is a non-zero mean vector, subtract x bar from it and get a 0 mean random vector. So, you are assuming that you have done all that and you have got a 0 mean random vector x available with you, right. And then we are defining that there is another m dimensional input vector which we are calling as q. Okay. So, we are assuming this to be an m dimensional unit vector. I will explain the significance of that. So, this is an m dimensional unit vector, dimension same as that of this x. This is m dimensional, this unit vector is also m dimensional. Now, what we want to do is that we want to project this x vector, the given x vector into this q dimensional this m dimensional unit vector space, something like this. That supposing we have got a 3 dimensional input vector, let us say we have got I, j and k available as input vector, and supposing we have got a point in space, which is having coordinate, let us say x, y, z. So, what we do? We, in order to represent this in the vector form, what we do is that we project this point into I direction, j direction and k direction. It is a projection that we get, and then we get ix, jy, kz, like that we get. So, essentially what we have to do in this case is that this is a 3 dimensional thing projected into a 3 dimensional unit vector space, and likewise here we have got an m dimensional random vector which we are projecting into an m dimensional unit vector. So, when we project it into now because it is unit vector, so one property that we must have is that the Euclidean norm of this q vector should be equal to 1. This is unit vector. So, now what we can represent is that the projection, when we consider the projection of the x vector onto q, if we are going to write that, let us say A is the projection, what will be the projection? X transpose q, very good. In fact, this is going to be a scalar quantity. It is a projection, so it is a scalar quantity, it is a dot product, that you said very rightly. So, it is x transpose q, this is the projection of x vector onto the q vector, the m dimensional input vector. Either you write it as x transpose q or you write it as q transpose x, it means one and the same. So, it is as if to say that projecting q into x or projecting x into q, anyway, either way it can be looked at, but this is the representation, and this we have subject to the norm of q vector equal to 1. So, the norm of q vector in this case can be written as what? It can be written as Q transpose Q. Okay, Q transpose Q, but Q transpose Q gives us norm of square. So, what we have to do is write it as Q transpose Q to the power half, okay, and this is equal to 1. So, this is the constraint on that vector, because this is a unit vector. So, that is why norm of Q equal to 1, and this is the projection. So, what we can write down now is that in the projected space, what is the expectation and what is its variance, all right. These two quantities we want to determine. So, given this, let us see what is going to be the expectation of A. A means the projected value, you mean to say. So, what is the expectation of A? Y 0? Yes. You see, expectation of A means expectation of this entire quantity x transpose Q. Okay. Now, naturally Q is not a random variable. So, Q comes out of the expectation operator. So, it is Q vector coming out and expectation of x, and what is expectation of x? That is equal to 0. So, it is quite obvious that this is equal to Q transpose expectation of x, okay, which is equal to 0. Okay. And what is the variance? The variance of this quantity is to be represented as the expectation of A square, right, and expectation of A square can be written as A square. How can we write A square? A square we can write as Q transpose x, this thing multiplied by x transpose Q. Is that right? Q transpose x, x transpose Q. So, this can be now represented as Q transpose and Q, they will be coming out of the thing. So, this is Q transpose, and within the expectation operator what are we going to have? It is going to be x x transpose, x x transpose, and this is going to be Q. Okay, this is Q transpose, this is Q. Now, what is this quantity? Expectation of, yes, it is the correlation. In fact, I mean it is x multiplied by x's outer product with itself. So, which is a correlation matrix of the x vector. Okay. So, this we are going to represent by the matrix R. This is going to be a matrix, right. This is an m by m matrix that results x x transpose. X is of dimension m. So, it is m by m vector, correlation vector. So, we are going to have it as Q transpose the correlation matrix R times Q vector, okay, where R is the correlation matrix, okay, given by R matrix equals expectation of x x transpose. Followed? Also, we note here that this correlation matrix, okay, will be obviously symmetric, right, because you are taking the same vector x and x transpose. X transpose is the different way of writing the x vector only. So, you are having absolutely symmetrical terms. So, that is why R transpose and R, they will be the same. Follow? And in fact, from the property of these sort of matrices, I mean which are similar matrices, properties of similar matrices also tells us that supposing we have got two vectors A and B which are of dimension m. Okay, we take two vectors of dimension m and those vectors are A and B. So, from this property, means from the symmetric property, from this property, it is possible for us to write A transpose R B vector. Okay. Do you know this? This is a very important property. A transpose R B is equal to B transpose R A. For symmetric matrix, it will be valid. All right. Now, okay. What we are more interested in is this expression. This is the variance expression, and what we want to do? We want to minimize the variance. Now, this correlation matrix is not exactly under our control, because this is controlled by the x vector itself. So, this is controlled by the random vector, the random process itself will control R. So, we do not have any control of that. So, what is in our hand in trying to design the minimum variance, in trying to have a minimum variance design? The proper choice of Q. That means to say that with a very proper and appropriate choice of Q, it is possible for us to go in for some form of minimization of this sigma square. So, this is what we should look for. That means to say that using the Q vector as a search, okay. If we use the Q vector as a search to find the minimum, in that case we can use the Q vector as if to say like a probe to find out that now you vary Q vector and find out that where do you find the minimum of the variance. All right. So, this variance sigma square that we have got, okay, is definitely some function of the Q vector. Okay. So, what we have to find out is that we have to find out a function psi of Q, okay, which is equal to this Q transpose R Q. So, I mean basically the Q that we are going to search through is a function like this. So, psi Q. So, we have to minimize this function psi Q. All right. So, this is exactly equal to sigma square. So, we write sigma square is equal to this equal to Q transpose R Q, and this we are going to write as our equation number 1. So, psi Q, okay, because we are finding out the variance based on this we are calling as the variance probe, because by varying this Q we are going to find out that where lies the minimum. So, at the point where these I mean psi Q has got some extremal values. Extremal values means in this case the extremal is definitely going to be in a minimal sense. The minimal will indicate the form of extremal that we are looking for, because I mean on the maximum side, yes, variance can reach anything, sky is the limit there. But for the minimum, yes, I mean there should be one extremal point that we are looking for. And at the point of extremal, what happens is that if the Q has already found out some extremal, in that case if we try to alter the Q slightly, if we perturb the Q vector, okay, from its minimal position Q, if we perturb the vector Q by an amount, let us say delta Q, okay, then at the place of extremal or at the place of minimum of the variance probe, we are going to have psi of Q equal to psi Q plus delta Q. Is that understood? So, at the for extremal values, for extremal or in this case minimal values, value of the variance, okay, what we should have is the psi of Q plus delta Q. What is the significance of this delta Q? I'll just explain it once more. This is equal to psi Q, and what is the significance of this? That means to say that Q is a vector which we have already found out to be a minimum. So, if Q is a vector which reaches the minimum of the variance, okay, in that case at the minimum if we try to perturb the vector Q slightly, okay, it will not change the variance much, because it has reached the bottom. So, if this is the variance probe, it has reached here. So, that means to say that if you try to disturb it little from q you want to disturb it to q plus delta q, the variance more or less remains the same.
This condition will be valid for local maxima also. How will you stop it?
But one thing, that local maxima don't arise. Okay, local maxima cannot arise in this case. Okay, because I mean from a set of data, okay, you can never try to achieve, because maxima is that I mean you can go anywhere in the maxima. Okay, you have to consider only the minimal thing, and for minimal you will get a point, I mean case arising like this.
You always be second order function.
Yes. So okay, I mean we will be coming to that. Okay, concepts will be little more clear later on. Okay, here there is a definite minimal existence that we are looking for. Okay, now if we assume this condition, okay, for the minimal, okay, then by the application, I mean from the very definition of the variance probe, because the variance probe what we have decided, yes, this is equal to q transpose r q, that is right. So q transpose r q, how do we write down? So if we write down q plus psi q plus delta q, if we want to write, then this becomes equal to psi q plus delta q, okay, transpose r, okay, times what, q plus delta q, followed, this transpose r then q plus delta q, by applying the same definition. Oh, so not psi, that is wrong. Yes, thank you very much for the correction. Yes, so this by applying the definition of equation 1 only, psi q plus delta q is equal to q plus delta q transpose r q plus delta q, right. So now what we have to do is to expand this, okay, expand this whole thing, and by expanding we will be getting a term like this. We will be getting in fact 3 terms. One is q transpose r q, this is one term. Then we will be getting 2 times delta q transpose r q, all right, and then we will be getting the third term as delta q transpose delta q, r delta q, correct, delta q times r delta q. Thank you for correction again. So there are 3 terms in this expansion. Okay. Now out of these 3 terms, okay, this one, that is delta q transpose r delta q, this term is not of significance. Why? Because delta q is a small perturbation that we have assumed, right. So delta q values itself being very small, okay, the contribution of this delta q transpose r delta q will be much less as compared to the contributions of the first 2 terms. So the first 2 terms will be dominating, and if we assume this extremal or the minimal condition over here, okay, then we can, okay, I mean one thing that I would like to say is that even if you, okay, let us say that for the sake of argument you treat it as extremal, okay, if the student finds it difficult to feel convinced that, I mean why can't we get a maximal, okay, let us say extremal, okay, let us proceed with the analysis, then we will study its minimal aspect in a better way. Now extremal if we take, then this condition is getting valid. So this term is equal to q transpose r q. So which means to say that if, I mean this thing we, I mean if we equate psi q plus delta q with psi q, In that case, this Q transpose RQ here and here getting cancelled. So, what we are getting is that this term anyway is neglected. So, this is equal to 0 and this gets cancelled with this. So, what remains is that delta Q transpose RQ is equal to 0, because psi q and psi q plus delta q are the same. Okay. So, this if we say equation number 2, so then what we obtain is that delta q transpose RQ is equal to 0. Anybody who found it difficulty in following this step? I may be going a bit too hurriedly, but tell me if anything you are missing. This is by comparing, I mean if we say that this is equation number 3, okay, then we can simply using equation 1 and 2 in 3. This is what we get, right, at the point of extremal. Now, this is let us say this one we are calling as equation number 4, right. Okay. Now, one thing is there that what we said in delta q, we have perturbed delta, we have perturbed q. Okay. By perturbing q, we have got p plus delta q. Now, one constraint that will always be followed is that because we have assumed q to be a unit vector, even after perturbation it has to remain as a unit vector only. Okay. So, that the Euclidean norm of q plus delta q should be equal to 1. Okay. So, what we enforce upon is that because q is a unit vector, so the norm of q plus delta q, the Euclidean norm of q plus delta q should be equal to 1, or equivalently, I mean we can express it as this squared if we take equal to 1. In that case, q plus delta q, that is the term, this transpose times q plus delta q should be equal to 1, all right. And now we can simply again we expand it and we find that what happens is this is q transpose q plus we will be having delta q transpose q plus again q transpose delta q, which are all the same. So, this will be 2 times delta q transpose q plus there will be a term delta q transpose delta q, which is again negligible term. This should be equal to 1. So, this is equal to 0, almost equal to 0, and q transpose q is equal to 1. So, this is equal to 1, which implies that this term is equal to 0, that is delta q transpose q is equal to 0. So, this is equation number 5. Okay. So, let us now remember that we have got an important condition from equation number 4 and we have got another important condition from equation number 5. And what is the physical significance conclusion from equation number 5? It means to say that q and delta q, they happen to be orthogonal. So, that means to say that only a change of direction of q is permitted. Okay. Orthogonal means that you can only change the direction of the q. So, this part we have to accept. Okay. And this one is already known to us, this is equal to 0. Now, since both of them are equal to 0, there must be some way of combining these two, but we find that there is some difference between this equation number 4 and equation number 5. And what is the difference? Here a term r is there, whereas here there is no such term, that is R. Now, Q as such is a dimensionless vector. I mean, Q's elements are not having any dimension, okay, because they are unit vectors. So, its elements are not having any dimension. So, the only dimension that is there is, I mean, in this equation whatever dimension we are getting is the dimension of the elements of R matrix, whereas in this case we do not have any such things. So, if we want to combinedly express this equation 4 and 5, we have to introduce a term, okay, which has got a dimension same as that of R. Okay. So, we can decide to introduce some factor, some multiple, or let us say some scalar quantity. Let us say that we introduce a scalar quantity lambda which is of dimension R. All right. If we can introduce a scalar quantity lambda which is having the same dimension as that of R, in that case this equation number 4 and equation number 5 can be combinedly written as this thing, this left hand side part plus or minus anything we can write, because lambda we choose as positive or negative, it depends upon that. Let us say that we choose as minus lambda times this is equal to 0. We can write that. So, let us write that and see what results. So, if we write that way, then delta q transpose R q minus lambda, lambda having the same dimension as that of the elements of R matrix, lambda delta q transpose q is equal to 0. Okay. Or equivalently, now we can write down that this is one and the same as writing, we take delta q transpose outside and write it as R q minus lambda q is equal to 0. Now, certainly delta q transpose is not 0. Okay. It is a non-zero quantity because we indeed wanted some perturbation. So, what we have got from the extremal condition is that necessarily this term has to be equal to 0. Okay. So, if we equate this term written within the square bracket to 0, in that case what results is R q is equal to lambda q. All right. Now, in this case you see dimensionally we do not have any problem, q is of dimension m, okay. Then R is of dimension m by m. So, this results in an m dimensional vector. Here lambda is a scalar, this q is an m dimensional vector. So, what results is simply equating the this thing, the RQ, simply equating very identical quantities. So, now we have got an equation like this and we call this as equation number 6, okay, where there is a definite relationship that we are getting between this R here on the left hand side and lambda on the right hand side. And this equation one should be able to solve, but it is not that this will be satisfied. A solution can be obtained for any values of lambda at any value of q. Given some R, given a matrix R, okay, we have to solve for a solution of this lambda and q. There will be some combinations of lambda and q that should result in this. So, what is the significance of this lambda? It is called eigenvalue, eigenvalue of the matrix R, that is right. Okay. So, lambda is called as the eigenvalue, lambda is eigenvalue of the matrix R, and R is of dimension m by m. So, how many such eigenvalues will be there? There will be m such eigenvalues. So, we can find out m such solutions. So, there will be lambda 1, lambda 2 up to lambda m, there should be m such solutions, okay, of eigenvalues, and the associated values of q's that we get with those are given as q1, q2 up to qm. These are the vectors which are associated with it. So, this lambda 1 to lambda m are the eigenvalues, and correspondingly all these q vectors to which space you are projecting the vector x, you are calling those things as eigenvectors. So, these are the eigenvectors. So, these are the eigenvalues and eigenvectors of the correlation matrix R. So, first of all we have to obtain the correlation matrix, that means to say that we definitely know the statistics of this x vector. Okay. So, now given that, I mean, if we can design these quantities, okay, in that case what results is that we will be projecting the x vector, okay, into a space that results in a low variance quantities. Okay. Now, actually speaking, there are, as we agreed, that there are m such solutions to equation number 6. So, we can write down in the following way. We can write down as R q j is equal to lambda j q j, okay, for j equal to 1 to up to m. Okay. And let the corresponding eigenvalues be arranged in the decreasing order. So, we place them in this order, that lambda 1 greater than lambda 2 up to, let us say here we have lambda j, the general term, and then last we have the lambda m. So, we have arranged them in a decreasing order. Okay. So, lambda 1 to lambda n, okay, so that lambda 1 is equal to lambda max. Okay. So, and then we use the eigenvectors to constitute a matrix. So, we now define a matrix capital Q which is composed of the individual eigenvectors. So, we have q1 vector, q2 vector, here qj vector, lastly qm vector. All right. So, how this definition helps? In that case, this one, let us say that this is equation number 7, where we have got m different such equations. Now, this m different such equations can be written in a more compact form by using this capital Q matrix representation. Okay. So, what results is R Q, I mean, if we write all these m equations in a combined way, in that case what results is R Q is equal to lambda, but do we get lambda? We get lambda 1 for the first one, we get lambda 2 for the second one, lambda 3 for the third one, and combinedly what do we get? We get a lambda matrix, and in which elements will those lambdas lie? In the diagonals. So, what we have here is this is equal to Q lambda matrix, okay, we call this as equation number 8, okay, where this capital lambda matrix that we are writing is equal to the diagonal elements of this lambda 1, lambda 2 up to lambda m. That is right. So, it is a diagonal matrix. So, if we write down it in the form of capital lambda matrix, okay, consisting of these diagonal elements, then this is the equivalent matrix representation of all these m different equations which we would have got otherwise. Okay. So, now one thing that one should note down from this is that what is the property of this Q matrix. You see, Q matrix is composed of all these different Q vectors, okay. And if we take the dot product, if we try to project one of these vectors into other, then what is it that we are going to get? 0. So, this is actually an orthogonal matrix. So, Q becomes an orthogonal matrix, and why? It satisfies the condition of orthonormality. Okay. So, we can say that the matrix Q is an orthogonal matrix, okay, which satisfies. So, this is orthogonal matrix satisfying, you take any column Q I, let us say you take the transpose of this and just take the dot product of this with Q j. You will find that this is equal to 1 when j is equal to I, and this is equal to 0 otherwise. So, for j not equal to I, this is equal to 0. So, Q is an orthogonal matrix, or to say from the orthogonality property we can write down that Q transpose Q is equal to identity matrix, because I mean this follows from this very basic property that because it is orthogonal, it results that Q transpose Q is equal to I, but we know that Q inverse Q is also equal to I, isn't it? Q inverse is equal to I. So, what it means is that Q transpose is Q inverse. Okay. So, from which we deduce that Q transpose is equal to Q inverse. Okay. So, that the equation that we have got, the equation number 8 that we had obtained, okay, just see, look very carefully. If we now pre-multiply both the left hand side and the right hand side by Q transpose, all right, then what results on the left hand side? Q transpose R Q, and what results in the right hand side? Q transpose Q, Q transpose Q lambda, and Q transpose Q is equal to identity matrix. So, what remains is the lambda. So, we can write, so from equation 8, using equation 8, we find what? Q transpose R Q, okay, is equal to the lambda matrix, right. So, this is the most compact matrix representation in equation number 9, which can be in the expanded form. We can write it down as, so in expanded form, the same thing, that is Q transpose R Q is equal to lambda, can be rewritten as Q j transpose R matrix Q k, that is equal to lambda j for k equal to j, and that is equal to 0 for k not equal to j. This is the expanded form of representation for equation number 9. Okay. And another thing that you should see is that this correlation matrix R itself, okay, could be expanded in terms of the eigenvalues. You just see that you can pre-multiply this by Q and you can post multiply that with Q transpose. If you do that, what results is the R matrix on the left hand side, and on the right hand side what results is the Q transpose lambda Q. Okay, lambda is just a diagonal matrix consisting of the scalar elements, and then we can represent the R matrix in the expanded form will be written as I is equal to summation I is equal to 1 to m lambda I qi transpose. Okay. This we can write as equation number 10. Okay. So, this is one thing which you can see is that from equation number 1 that we had got. Okay, from the equation number 1 that we had got, that psi of q, okay, psi of q is equal to q transpose r q, okay, and q transpose r q is equal to what? It is equal to lambda j. So, also we find here that psi q j, which are the variance probes, okay, that is equal to lambda j. So, the variance probes that we have got are actually the eigenvalues of the correlation matrix. So, this is another important relation. So, this much for today's class. Okay, we will continue with the mathematical analysis and the development of the theory in the next class. Thank you.